Hello friends, welcome to my channel. This is most important portion of fluid mechanics part 5 for Isro 2017 examination. In this video I will cover impact of jet part and fluid machines. Fluid machines, turbine and pumps I will cover. In impact of jet, first jet is striking on a stationary vertical flat plate. So, Fx is the rate of change of momentum in the direction of force. Its initial momentum minus final momentum divided by time. So, mass per time into initial velocity minus final velocity. We know momentum is m1 v1 minus m2 v2. So, here we are applying initial velocity in the direction of jet is v, then final velocity in the direction of jet is 0. So finally we will get Fx equal to rho a v square. In problem they will ask this question. You have to use this formula. Force in the direction of jet for a stationary vertical flat plate. When jet is strikes on a moving plate is moving with velocity small u and jet velocity is capital V. So relative velocity of jet with respect to plate is V minus small u. Then mass flow rate m dot is mass of water striking on the plate per second is rho a into relative velocity is V minus u. Then Fx equal to force by the jet on the direction of jet. Once they asked this question in Isro examination, so this is very important. Here m dot is rho a, then V minus u. Initial velocity is V minus u in the direction of jet, and in the direction of jet final velocity is 0. So Fx is rho a v minus u square. This formula we have to use in solving problems. When jet strikes on a series of vanes, that condition m dot equal to rho a v, then force in the direction of jet Fx is m dot into initial velocity minus final velocity. M dot is rho a v and initial velocity is v minus u in the direction of jet, and final velocity in the direction of jet is 0. So Fx is rho a v into v minus u. Here one more thing is important. For maximum efficiency, u small u equal to v by 2. V is velocity of jet striking on the plate or vane. U is the velocity of the vanes. And maximum efficiency is 50%. This is same condition applicable to Pelton wheel also. Once they ask this question, for maximum efficiency, what is the condition of jet ratio or small u by capital V? For jet propulsion, one question they asked from this jet propulsion. Here V is velocity of jet coming out of the orifice, V equal to Cv into root over of 2gh, and m dot mass flow rate is rho a v, and force acting on the water coming out through the orifice is Fx equal to m dot into change in velocity. So it's rho a v into v minus 0. So rho a v square. And force on the tank, for here relative velocity we have to calculate. Force on water is in this direction, reaction force is in this direction. So force on the tank Fx equal to rho a into V plus U, in this direction V, so reaction in this direction, so V plus U they will add, V plus U, and initial velocity is V plus U minus small u is the final velocity, and finally we will get rho A V plus U into V. This is Fx. This formula we have to use. Then turbine. Turbine, mainly theory is important for Pelton wheel, Francis turbine and Kaplan turbine. Pelton wheel is example of impulse turbine, tangential flow, high head and low discharge and low specific speed. For Francis turbine, it's reaction turbine, inward flow reaction turbine, medium head, medium discharge and medium specific speed. And next Kaplan turbine. In Kaplan turbine, blades are adjustable, reaction turbine, axial flow turbine, low head and high specific speed. But in Pelton wheel, the head is 250 meter above. For Francis turbine, it's 60 to 250 meter, and for Kaplan turbine, it's below 60 meter. Below 60 meter, it's above 250 meter. Here in force on series of vanes, same as Pelton wheel, speed ratio question they asked 3 times, rho equal to u by v. You have to calculate. They will give u and v, or v is 2gh root over u is pi dn by 60. Then you have to calculate speed ratio, or they will give speed ratio, you have to calculate small u or capital V. For efficiency, for Pelton wheel, efficiency is maximum, formula also important, 1 plus cos phi by 2, and condition I already told, u equal to v by 2. Both are important here. And discharge through turbine is also important. Discharge through turbine is pi d1 b1 vf1 equal to pi d2 b2 vf2. This formula also important. Then unit speed nu equal to n by root h, and unit discharge is q by root h, and unit power is p by h to the power 3 by 2, and specific speed for turbine it's ns equal to n root p h to the power 5 by 4. Here one thing you have to remember, p is in kilowatt. This is important. And model laws also important. For model laws, discharge is proportional to n, and head is proportional to n square, and power is proportional to nq. One more thing is important here. Discharge is proportional to dq, or diameter q, or head is proportional to d square, and here power is proportional to d to the power 5. From here you will get p by nq, d to the power 5 is constant, and h by n square d square equal to constant, q by n dq is constant. Using this relation you have to solve the problems. And for pump, specific speed is ns equal to, in terms of q it will come n root q h to the power, its manometric head, hm to the power 3 by 4. And its curve also important. Power, head and discharge q versus speed. or N. Here Q is directly proportional to N. It will go like this, and for head it's N square, and for power it's NQ. Q is proportional to N square, power proportional to NQ. And for turbine, operating characteristic curves is important, or constant speed curve, efficiency and power versus discharge. It will go, for efficiency it will increase up to certain point, after that and it will decrease. And for power it will go on increase, after certain point it will decrease. This is for power and this is for efficiency. Head is constant and speed is constant. And for pump, operating characteristic curve, once they ask this question, efficiency, power and head versus discharge. For pump, head will come like this. It will decrease with discharge. If discharge will increase, then head will decrease. This is head. And for efficiency, it will go on increase, after certain point it will decrease. This is for efficiency. And for power, it will increase, after certain point it will decrease. This is for power. So this is the end of. One more thing is important. Cavitation. Thomas cavitation parameter. Cavitation theory also important. Once they ask Thomas cavitation parameter, that formula also important. Cavitation theory, you check it from book. Only definition you check. And for Thomas cavitation parameter, this is the formula. Sigma C equal to P minus PV by half rho V square. One question I already solved for this in my previous videos. You can check it from my playlist. So you just remember this formula. They will ask problem. And draftive theory also you can check. That is also important. So this is the end of fluid mechanics paper and fluid machines. Thank you friends. Thank you for watching my video. Thank you.